Gearswitch does not provide the same level of protection as ground fault circuit interrupter. GFCI receptacles. GFCI receptacles are designed to protect against ground faults by monitoring the current flowing to and from an electrical device. If there is an imbalance, indicating current leakage to ground, the GFCI trips, quickly cutting off power to prevent electrical shock. Gearswitches, on the other hand, are primarily used to switch between different power sources, such as utility power and a backup generator. They ensure a smooth transition during power outages, maintaining a continuous power supply. The fundamental difference lies in their purpose and operation. GFCI receptacles are focused on personal safety by detecting and interrupting ground faults. Gearswitches are focused on power continuity by switching between available power sources. To understand this further, let's delve into the principles of GFCI operation. A GFCI constantly monitors the current in the hot and neutral wires of a circuit. Under normal conditions, the current flowing through both wires should be equal. If there's a ground fault, some current leaks to ground, creating an imbalance. This imbalance is detected by the GFCI's internal circuitry, which then trips the circuit, typically within milliseconds. This rapid response is crucial in preventing electrical shock, as even a small amount of current can be dangerous. Now let's consider the function of a gearswitch. A gearswitch is a manually operated or automatic transfer switch that allows switching between different power sources. In a hospital setting, this is essential to ensure that critical equipment and systems continue to operate during power outages. The gearswitch connects the building's electrical system to either the utility power grid or a backup generator. When utility power is lost, the gearswitch automatically or manually switches to the generator, providing a seamless transition. The gearswitch itself does not provide ground fault protection. It simply redirects the flow of power from one source to another. While the circuits powered by the gearswitch may have overcurrent protection, such as circuit breakers or fuses, these devices are designed to protect equipment from damage due to excessive current, not to protect people from electrical shock due to ground faults. In a hospital, specific areas are required to have GFCI protection. These areas typically include locations where there's a high risk of electrical shock, such as bathrooms, patient care areas, and operating rooms. The National Electrical Code (NEC) specifies the requirements for GFCI protection in healthcare facilities. The NEC Section 517.20 covers the general requirements for essential electrical systems in healthcare facilities, but it doesn't replace the need for GFCI protection in areas specified by other NEC sections. For example, NEC Section 210.8 specifies where GFCI protection is required in dwelling units and other locations, which may also apply to certain areas within a hospital. Therefore, even if a section of a hospital is on a gearswitch, GFCI protection is still required in areas where it's mandated by the NEC. It's important to note that the presence of a gearswitch does not negate the need for proper wiring and grounding throughout the electrical system. A properly grounded electrical system provides a low impedance path for fault current to flow back to the source, allowing overcurrent protection devices to trip and clear the fault. However, grounding alone does not provide the same level of protection as GFCI receptacles. Grounding is primarily intended to protect equipment from damage, while GFCI receptacles are primarily intended to protect people from electrical shock. The installation and maintenance of electrical systems in hospitals are subject to strict regulations and standards. These regulations are designed to ensure the safety of patients, staff, and visitors. It is crucial that all electrical work is performed by qualified and licensed electricians who are familiar with the applicable codes and standards. Regular inspections and testing of electrical systems are also essential to identify and correct any potential hazards. This includes testing of GFCI receptacles to ensure they are functioning properly. GFCI receptacles should be tested monthly to verify that they trip when a ground fault is simulated. This can be done using a GFCI tester, which is a simple device that plugs into the receptacle and injects a small amount of current to ground. If the GFCI does not trip, it should be replaced immediately. Furthermore, hospitals often employ redundant electrical systems to enhance reliability and safety. This may include multiple power sources, backup generators, and uninterruptible power supplies (UPS). These systems are designed to ensure that critical equipment continues to operate even in the event of a power outage or other electrical fault. Redundant systems do not replace the need for GFCI protection. GFCI receptacles are still required in areas where they are mandated by the NEC, regardless of the presence of redundant systems. In summary, a Gearswitch is a device that switches between power sources, while a GFCI receptacle is a device that protects against ground faults. They serve different purposes and provide different types of protection. The presence of a Gearswitch does not eliminate the need for GFCI protection in areas where it's required by the NEC. To reiterate, Gearswitches provide power continuity while GFCI receptacles provide localized ground fault protection. The NEC mandates GFCI protection in specific areas of hospitals for safety. Regular testing and maintenance of electrical systems, including GFCI receptacles, is essential. To add some clarification, let's consider a scenario where a piece of medical equipment is plugged into a GFCI protected receptacle in a patient care area. If a ground fault occurs in the equipment, the GFCI will trip, immediately cutting off power to the equipment and preventing electrical shock to the patient or staff. Now, let's consider the same scenario, but without GFCI protection. If a ground fault occurs, the current will leak to ground, potentially causing electrical shock. The circuit breaker may not trip, as the fault current may not be high enough to exceed the breaker's rating. This is where the danger lies, as even a small amount of current can be lethal. The GFCI is designed to detect these small ground fault currents and trip before they can cause harm. In addition to patient care areas, GFCI protection is often required in other areas of a hospital, such as laboratories and kitchens. These areas are also subject to a high risk of electrical shock due to the presence of water and other conductive materials. The NEC provides specific guidelines for GFCI protection in these areas. The NEC Section 517.21 discusses the wiring and protection requirements for patient care areas. This section references other NEC articles that specify the requirements for GFCI protection in specific locations. It's important to consult the NEC to determine the specific requirements for GFCI protection in each area of a hospital. It should be emphasized that GFCI receptacles are not a substitute for proper wiring and grounding. A properly wired and grounded electrical system is essential for safety, regardless of the presence of GFCI receptacles. However, GFCI receptacles provide an additional layer of protection that can significantly reduce the risk of electrical shock. Think of it this way: a properly grounded system offers overcurrent protection, but a GFCI adds a layer of protection for the person, not the equipment. In conclusion, while a Gearswitch ensures power continuity, it doesn't offer the same shock protection as GFCI receptacles. GFCI protection is vital in areas of hospitals where electrical hazards are higher, as mandated by the NEC. Regular inspections, testing, and maintenance of both the Gearswitch system and GFCI receptacles are crucial for a safe electrical environment. Understanding these differences and adhering to electrical safety codes ensures the well-being of patients and staff in a hospital setting. Remember that electrical safety is a critical aspect of healthcare facility management. It requires a comprehensive approach that includes proper design, installation, maintenance, and training. By implementing these measures, hospitals can minimize the risk of electrical hazards and ensure a safe environment for everyone. Moreover, let's consider the evolution of electrical safety standards and the increasing emphasis on GFCI protection. Over the years, electrical codes have become more stringent in their requirements for GFCI protection, reflecting a growing awareness of the dangers of electrical shock. The widespread adoption of GFCI receptacles has significantly reduced the number of electrical injuries and fatalities. This trend is expected to continue as technology advances and new safety measures are developed. The use of arc fault circuit interrupters (ASIs) is also becoming more common in residential and commercial buildings. ASIs are designed to protect against arc faults, which are another type of electrical hazard that can cause fires. While lift size are not typically required in hospitals to the same extent as GFCI receptacles, they may be used in certain areas to enhance safety. Arc faults are unintentional electrical discharges that occur when current flows through an unintended path. These faults can generate high temperatures and ignite flammable materials, leading to fires. Size detect arc faults and trip the circuit, preventing fires from starting. The combination of GFCI receptacles and F-size provides a comprehensive approach to electrical safety, protecting against both shock and fire hazards. To further illustrate the importance of GFCI protection, let's consider the scenario of a patient using an electrical device in their hospital room. The device may be a personal item, such as a hairdryer or electric shaver, or it may be medical equipment, such as an room and floor pump or patient monitor. If the device has a ground fault, the GFCI receptacle will trip, protecting the patient from electrical shock. Without GFCI protection, the patient could be exposed to a potentially lethal electrical current. Hospitals are particularly vulnerable to electrical hazards due to the presence of numerous electrical devices, wet environments, and patients with compromised immune systems. Electrical shock can be especially dangerous for patients who are already ill or weak. For these reasons, it's essential that hospitals implement and maintain robust electrical safety programs. These programs should include regular inspections, testing, and maintenance of electrical systems, as well as training for staff on electrical safety procedures. In addition to GFCI receptacles and F-size, other electrical safety devices and practices can help to reduce the risk of electrical hazards in hospitals. These include surge suppressors, which protect against voltage spikes, and isolation transformers, which isolate electrical circuits from the power source. Proper grounding and bonding are also essential for electrical safety. Grounding provides a low-impedance path for fault current to flow back to the source, allowing overcurrent protection devices to trip and clear the fault. Bonding connects all metal parts of the electrical system together, preventing voltage differences that can cause electrical shock. The NEC provides detailed requirements for grounding and bonding in healthcare facilities. These requirements are designed to ensure that the electrical system is safe and reliable. In addition to following the NEC requirements, hospitals should also consider implementing best practices for electrical safety. These practices may include using qualified and licensed electricians, conducting regular electrical safety audits, and providing ongoing training for staff. By taking these steps, hospitals can create a culture of electrical safety that protects patients, staff, and visitors from electrical hazards.